inside the largest war factories, full process. This is the story of the most manufactured item in human history. During World War II, the United States produced over 41 billion rounds of ammunition. That's 41,000 million bullets, shells, and cartridges. Enough ammunition to circle the Earth twice if laid end to end. This is how America fed the guns of freedom, from raw materials to the battlefield. This is the complete process of wartime ammunition production. Our story begins in the copper mines of Montana and Arizona, where some of the richest copper deposits in the world have been mined since the 1800s. Copper is the foundation of every cartridge case because it's strong, malleable, and doesn't spark when struck. The Anaconda Copper Mine in WWII, Montana operates 24 hours a day, with miners working in shifts to extract copper ore from shafts that descend over a mile underground. The ore is blasted loose using dynamite, then loaded into rail cars that carry it to the surface. At the surface, the ore goes through massive crushers that break the rock down into gravel-sized pieces. This crushed ore is then sent through a concentration process that uses water, chemicals, and flotation tanks to separate the copper minerals from worthless rock. The concentrated copper ore, now containing about 30% copper, is shipped by rail to smelters. Simultaneously, lead is being mined in Missouri, the lead belt of America. Lead is essential for bullet cores because it's dense, soft enough to expand on impact, and melts at relatively low temperatures for easy casting. The lead ore, called galena, is mined from underground operations similar to the copper mines. The ore is crushed and concentrated, then shipped to lead smelters, where it's melted and refined to 99.9% purity. The copper concentrate arrives at smelters in Anaconda, Montana, and El Paso, Texas. Here, massive reverberatory furnaces melt the concentrated ore at temperatures exceeding 2,000 degrees Fahrenheit. The molten copper settles at the bottom, while impurities float to the top as slag. This crude copper, called blister copper, because of its appearance, is about 98% pure, but needs further refinement. The blister copper is transferred to converter furnaces where air is blown through the molten metal, burning away sulfur and other remaining impurities. Then it goes to the final refining stage, electrolytic refinement. Large slabs of crude copper are suspended in tanks filled with copper sulfate solution. Electric current passes through the solution, causing pure copper to deposit on cathodes, while impurities fall to the bottom. The result is copper that's 99.99% pure, exactly what's needed for cartridge cases. The refined copper is cast into large ingots, weighing several hundred pounds each. These ingots are reheated in massive furnaces until they're glowing orange, then fed into rolling mills. These mills are engineering marvels, with enormous rollers that squeeze and stretch the copper like taffy. The copper passes through the rollers multiple times, each pass reducing its thickness and increasing its length. What started as a thick ingot becomes a sheet of copper, just a few thousandths of an inch thick. The copper sheets are annealed, a heat treatment process that makes the metal soft and workable again after the rolling has hardened it. Then they're cleaned in acid baths that remove any oxidation and scale, leaving bright, clean copper ready for the next stage. These cleaned sheets are rolled onto enormous spools, each containing thousands of feet of copper strip. The spools are loaded onto trucks and shipped to ammunition factories. Now we enter the cartridge case factories, massive facilities built specifically for war production. The Lake City Army Ammunition Plant in Missouri is one of the largest, covering nearly 4,000 acres. At peak production, this single facility employs over 20,000 workers and produces millions of rounds every single day. Most of these workers are women, filling roles left vacant by men fighting overseas. They're known as ammunition girls, and their precision work is vital to the war effort. The copper strip arrives at the blanking presses, massive machines that stamp out circular discs called blanks. Each press operates with tremendous force, punching hundreds of blanks per minute from the moving copper strip. The remaining strip, now full of holes like Swiss cheese, is collected and sent back to the smelters for recycling. Nothing is wasted. Every scrap of copper is precious and must be reused. The blanks move to the cupping presses where they're transformed from flat discs into shallow cups. This is the first step in drawing the cartridge case. The blank is placed between a punch and a die, and tremendous pressure forces the copper to flow into the shape of a cup. The metal stretches and thins during this process, and the atomic structure of the copper itself changes, becoming harder and more brittle. These cups go through multiple drawing operations, each one making the cup deeper and the walls thinner. For a .30 caliber rifle cartridge, there might be 5 or 6 drawing operations. Each operation requires a different set of dies, precisely machined to tolerances of 10/1000ths of an inch. The cups pass from press to press down a production line, getting longer and narrower with each step. Between drawing operations, the cases must be annealed again. The work hardening from drawing makes the copper brittle and prone to cracking. Annealing softens it so it can withstand the next drawing operation. The cases travel through long furnaces on conveyor belts, heated to precise temperatures, then cooled. After annealing, they're cleaned in tumbling barrels filled with an abrasive media that polishes away any scale or discoloration. After the final drawing operation, the cases look almost like finished cartridge cases, but they need trimming. The mouths of the cases aren't perfectly even after drawing, so they pass through trimming machines that cut them all to exactly the same length. For a .30-06 rifle cartridge, that length is 2.494 inches, and it must be accurate to within a few thousandths of an inch. Next comes head stamping. The base of each cartridge case is stamped with identifying information: the caliber, the manufacturer's mark, and the year of production. These stamps are applied by powerful presses that literally press the information into the solid brass base. The stamps are small, but must be clear and legible, because they identify the ammunition for decades to come. The primer pocket must be formed in the base of the case. A special press punches a precisely sized and shaped pocket that will hold the primer. The flash hole, a tiny opening that allows the primer's flame to reach the powder charge, is also punched at this stage. These operations require perfect alignment, because if the flash hole isn't centered or is the wrong size, the cartridge won't fire reliably. The inside of the case is inspected using gauges and optical instruments. Any case with cracks, splits, or excessive thinning is rejected and sent back for remelting. Quality control is rigorous because a defective case can cause a weapon to malfunction or even explode, potentially killing the soldier using it. Inspectors check hundreds of cases per hour, and they take their responsibility seriously. The case mouths need to be tapered and sized precisely. For rifle cartridges, the neck that will hold the bullet is made slightly smaller in diameter than the bullet itself. When the bullet is pressed in, the brass grips it tightly. The cases pass through sizing dies that squeeze the neck to the correct diameter. Then the case mouth is slightly flared outward to make bullet insertion easier during the loading process. While the cases are being manufactured, bullets are being produced in a separate section of the factory. Most rifle and machine gun bullets have a lead core surrounded by a copper jacket. The process starts with lead ingots being melted in electric furnaces. The molten lead is cast into cylindrical cores using precision molds. These cores cool and solidify into slugs that are roughly the shape and weight of the finished bullet. The lead cores are then swagged, pressed in powerful dies that compress them to exact dimensions and weight. Every core must weigh exactly the same, typically to within a fraction of a grain. A grain is a unit of weight used in ammunition, with 7,000 grains equaling 1 pound. For a .30 caliber rifle bullet weighing 150 grains, the lead core might weigh about 140 grains, with the jacket making up the difference. The copper jackets start as small cups, stamped from copper strip in a process similar to making cartridge cases. These cups are drawn through multiple dies until they're the right length and thickness. The jacket must be thick enough to prevent the bullet from deforming when it hits the rifling in the gun barrel, but thin enough to allow controlled expansion when it hits a target. The lead core is inserted into the copper jacket. and then the two components are pressed together in a swaging die. This operation fuses the core and jacket into a single unit and forms the bullet's final shape. For pointed bullets, the nose is formed in this swaging operation. The die shapes the jacket around the core with tremendous precision, creating the ogive, the curved nose shape that gives the bullet its aerodynamic properties. The base of the bullet is also formed during swagging. Some bullets have a boat tail, a tapered base that reduces air drag and improves long-range accuracy. Others have a flat base. The choice depends on the bullet's intended use. Machine gun bullets typically have boat tails for better long-range performance. Pistol bullets usually have flat bases because they're used at shorter ranges where aerodynamics matter less. After swagging, the bullets are cleaned and inspected. They pass through automated weighing machines that check each bullet's weight. Any bullet that's even a single grain too heavy or too light is rejected. They also pass through gauges that check diameter, length, and shape. The inspection process is so thorough that defective bullets rarely make it to the loading line. Now we move to the propellant manufacturing facilities. Gunpowder for World War II ammunition isn't black powder, like in the old days. It's smokeless powder, a much more powerful and efficient propellant. There are two main types used: single-base powder made from nitrocellulose, and double-base powder made from nitrocellulose and nitroglycerin. Both are extremely dangerous to manufacture. The process starts with cotton linters, the short fibers that remain on cotton seeds after ginning. These fibers are almost pure cellulose. The cotton is treated with a mixture of nitric acid and sulfuric acid in a process called nitration. This converts the cellulose into nitrocellulose, a compound that contains a lot of chemical energy. The nitration process is carefully controlled because nitrocellulose is sensitive to heat and shock. After nitration, the nitrocellulose is washed repeatedly to remove all traces of acid. Any remaining acid would cause the powder to deteriorate over time and could cause spontaneous combustion. The washed nitrocellulose looks like wet cotton and is stored underwater for safety until it's needed for the next stage. For double-base powder, nitroglycerin is added to the nitrocellulose. Nitroglycerin is one of the most dangerous substances manufactured during the war. It's made by carefully adding glycerin to a mixture of nitric and sulfuric acids. The reaction generates tremendous heat and must be done in small batches with constant cooling. Workers who make nitroglycerin follow strict safety protocols because any contamination or overheating can cause an explosion. The nitrocellulose and nitroglycerin, if used, are mixed with solvents like acetone and various stabilizers that prevent deterioration. This mixture is blended in mechanical mixers until it forms a dough-like consistency. The mixing buildings are located far apart from other buildings and have walls designed to direct any explosion upward rather than outward. The powder dough is then pressed through dies in a process called extrusion. The dies have small holes that shape the powder into specific forms. For rifle powder, it might be extruded as tiny cylinders or flattened strips. For artillery powder, it's formed into larger grains or even multi-perforated tubes. The shape of the powder grain affects how fast it burns, which controls the pressure curve in the gun barrel. The extruded powder is cut to the right length, then dried in temperature-controlled rooms. As the solvents evaporate, the powder hardens into its final form. The drying process takes several days and must be done gradually to prevent the powder grains from cracking or deforming. After drying, the powder is coated with graphite to reduce static electricity and prevent the grains from clumping together. Every batch of powder is tested before it's approved for use. Sample batches are burned in pressure vessels that measure how fast the powder burns and how much pressure it generates. The powder must meet strict specifications for burning rate, energy output, and consistency. Even small variations can affect accuracy and safety, so quality control testing is extensive. The approved powder is packaged in metal cans or kegs and stored in magazines, special buildings designed to contain explosions. The magazines are earth-covered bunkers, spaced far apart, so that if one explodes, it won't set off a chain reaction. The powder is stored here until it's needed on the loading lines. Now we need primers, the small but critical components that ignite the powder charge. Primers are manufactured in some of the most dangerous areas of the ammunition plant. A primer consists of a small brass or copper cup containing a pellet of primary explosive compound. This compound is extremely sensitive and can be detonated by a sharp blow, friction, or even static electricity. The primer compound is a mixture of lead styphnate, barium nitrate, antimony sulfide, and other chemicals ground together into a fine powder. This mixing is done remotely in small batches, often by machines controlled from behind protective barriers. Workers who handle primer compounds wear special non-sparking shoes and work on conductive floors to prevent static buildup. Even a tiny spark can cause a deadly explosion. The primer cups are stamped from brass strip, similar to cartridge cases, but much smaller. These cups are about the size of a pencil eraser for a rifle cartridge. The primer compound is pressed into the cups in measured amounts, typically just a few grains. The pressing operation is done by machines that apply exact pressure to consolidate the compound into a firm pellet. An anvil, a small piece of brass with a point on it, is pressed into the primer on top of the compound. When the firing pin strikes the primer, it crushes the primer compound against this anvil point, causing it to explode. The flame from this explosion shoots through the flash hole in the cartridge case and ignites the main powder charge. It all happens in a few thousandths of a second. The completed primers are moved to the loading area in small quantities for safety. They're kept in special containers that limit any explosion to a small area. Workers on the loading lines handle primers with respect, knowing that these tiny components are responsible for hundreds of accidental explosions in ammunition plants every year. Finally, we reach the loading lines, where all the components come together. This is where cases, bullets, powder, and primers are assembled into finished cartridges. The loading lines are marvels of mechanization, with dozens of machines performing operations in precise sequence. At peak production, a single line might assemble 10,000 rounds per hour. The empty cartridge cases arrive at the loading line in large bins. They're fed into the first machine, which inserts the primers. The machine picks up a case, positions it precisely, picks up a primer, and presses the primer into the primer pocket with exactly the right amount of force. Too little force, and the primer might fall out. Too much, and it might be crushed or even detonated. The machine accomplishes this delicate task hundreds of times per minute. After priming, the case is moved to the powder charging station. This is one of the most critical operations because the powder charge must be exactly right. Too little powder, and the bullet won't reach its target with enough velocity. Too much, and the pressure in the gun barrel could be dangerously high. The charging machines use volumetric measures that drop a precise amount of powder into each case. For rifle and machine gun ammunition, the typical powder charge is between 40 and 50 grains, depending on the specific cartridge. The powder flows from hoppers through tubes into the waiting cases. After charging, each case passes under a sensor that checks whether it's been charged. Empty cases or double charges are automatically rejected from the line. The loaded cases move to the bullet seating station. Here, bullets are pressed into the case mouths to a precise depth. The seating depth affects the pressure when the cartridge is fired and must be consistent from round to round for good accuracy. The bullets are held in feeders that orient them correctly and present them to the seating die. The die presses the bullet into the case with several hundred pounds of force, and the brass neck grips the bullet tightly. For some ammunition types, the case mouth is crimped around the bullet to hold it even more securely. This is especially important for machine gun ammunition, which will be subjected to rough handling and high forces during feeding and chambering. The crimp is applied by dies that press the case mouth into a groove around the bullet, or fold it inward against the bullet. The finished cartridges now pass through a final inspection station. Automated gauges check the overall length of each cartridge. They must all be exactly the same length, so they'll feed reliably through the weapon and fit in the chamber correctly. Any cartridge that's too long or too short is rejected. Visual inspectors also examine the cartridges for defects, like dented cases, crooked bullets, or missing primers. After inspection, the cartridges are ready for packaging. Small arms ammunition is typically packed in 20-round cartons for rifle ammunition or 50-round boxes for machine gun ammunition. The cartons are packed into larger wooden crates or metal ammunition cans. For long-term storage, the cans are sealed and marked with the type of ammunition, lot number, and date of manufacture. Machine gun ammunition is also assembled into belts. For the .30 caliber Browning machine gun, cartridges are loaded into disintegrating metal links that hold them in a belt. As the gun fires, the links separate and fall away, leaving just the empty cases. Belt loading is done by specialized machines that pick up cartridges and links and snap them together and produce completed belts that can be hundreds of rounds long. Artillery ammunition follows a similar but scaled-up process. Artillery shells start as steel forgings, large cylinders of steel that are machined and heat-treated to form the shell body. The shell body is much thicker than a cartridge case because it must withstand the enormous pressures of artillery firing and also survive the impact if it's an armor-piercing shell. The shell body is threaded at one end to accept a fuse and has a base plug threaded into the other end. The interior is hollow and will be filled with explosive. High-explosive shells are filled with TNT, a powerful explosive made from toluene and nitric acid. The TNT is melted and poured into the shell in liquid form, then allowed to cool and solidify. This is dangerous work because molten TNT is sensitive to shock. After filling, the fuse is screwed into the nose of the shell. Fuses come in many types: point-detonating fuses that explode on impact, time fuses that explode after a set delay, and proximity fuses that use radio waves to detect when they're near a target. Each fuse is a precision instrument, manufactured to exacting standards. The completed shells are painted with color codes that identify their type. High-explosive shells are painted olive drab with yellow markings. Armor-piercing shells are black with white markings. Smoke shells are light green. These color codes allow soldiers to quickly identify the right ammunition for their mission. Artillery propellant charges are packaged separately in cloth bags or brass cases, depending on the size of the gun. For large naval guns, the propellant might come in bags containing hundreds of pounds of powder. For smaller field artillery, the propellant is loaded into brass cases, similar to rifle cartridges, but much larger. The completed ammunition, whether small arms or artillery, is stored in ammunition depots spread across the country. These depots are carefully designed with earth-covered magazines, spaced far apart. The ammunition is stored by type and lot number, with meticulous records kept of every item. Temperature and humidity are controlled to prevent deterioration. From the depots, ammunition moves by rail and ship to ports, where it's loaded onto cargo vessels. The loading process is carefully supervised because ammunition ships are prime targets for enemy action. The ships join convoys crossing the Atlantic, protected by warships against U-boat attacks. Many ammunition ships are lost to torpedoes, their explosions so violent they vaporize the entire ship and any vessels nearby. Ammunition that survives the crossing is unloaded at ports in Britain or France and moved to forward supply dumps. From these dumps, trucks carry it to units at the front. Artillery batteries might receive hundreds of shells per day during heavy fighting. Infantry units receive thousands of rounds of rifle and machine gun ammunition. At the front lines, soldiers break open the crates and load magazines, belts, and clips. A rifle squad might carry 2,000 rounds of ammunition between them. A machine gun team carries thousands more. Artillery crews stack shells in ready racks next to their guns, prepared to fire hundreds of rounds in support of an attack. When the trigger is pulled or the lanyard yanked, all of this manufacturing effort reaches its culmination in a fraction of a second. The firing pin strikes the primer. The primer compound explodes, sending a jet of flame through the flash hole. The powder charge ignites and burns incredibly fast, generating hot gases that expand with tremendous pressure. This pressure pushes the bullet or shell down the barrel, spinning it with the rifling to stabilize its flight. The bullet or shell leaves the barrel at speeds ranging from 800 feet per second for pistol ammunition to over 3,000 feet per second for high-velocity rifle rounds. Artillery shells can exceed 5,000 feet per second. The projectile flies toward its target, carrying the kinetic energy created by all those manufacturing processes. All that industrial might, all that American productivity. By the end of World War II, American ammunition factories have produced over 41 billion rounds of small arms ammunition, over 1 billion artillery shells, and hundreds of millions of mortar rounds, grenades, and other munitions. This represents the largest manufacturing effort in human history up to that point. Every round required copper from Montana, lead from Missouri, cotton from the South, chemicals from dozens of plants, and the labor of hundreds of thousands of workers. The ammunition girls, the miners, the metal workers, the powder makers, the inspectors, and the packers all knew they were doing essential war work. Every defective round they caught might save a soldier's life. Every extra round they produced might make the difference in a battle. They worked long hours in dangerous conditions, and many paid with their lives in industrial accidents. This is how World War II ammunition was made, from mines and fields to the battlefield, a complete industrial process that transformed raw materials into the tools of victory. It's a story of American industrial might, of engineering excellence, of quality control and mass production, and of the workers who made it all possible. They didn't carry rifles, but they helped win the war just the same.